recording. So for part B of the number 2, we have the graph. We have to find the region between among these three graphs. So y equals e to the power x. E to the power x, the typical graph of the e to the x is the exponential graph. The e to the negative x, if we look at one piece at a time, e to the negative x is the 1 over e to the x, or it's in opposite way, kind of the flip of the graph from the left to the right to the left. And then with the number 2, that is the stretching part, the stretch or the factor to the graph of the e to the negative x. And then added by 1. Added by 1, that means the graph is up by 1 unit. For x equals 0, x equals 0 is the vertical line or the y-axis. So this one is the y-axis. When you put all of them together, I'll show you real quick. The graph will look like this. So the e to the x, we know that the property, the intercept is 0, 1. For the 2e to the negative x plus 1, the intercept is 0, 3. And the line x equals 0, that's the y-axis. So this is x equals 0. These three graphs meet, and then the region appears when they all three live bounded. I mean, they're all together. So your goal is to find this area. The problem is, what is the intersection point of the two exponential graphs? What you would do, you do the same as before. You set up the equations like by letting the e to the x equals 2e to the negative x plus 1, and then solve for x to find the intersection point. Okay, that means you're gonna deal with the exponential function. You might not like to deal with the exponential, not as much as when you deal with the polynomial, but don't worry, it can be done. For this problem, 9 tips that can share with you: change the negative side to positive side, or the other way, you make the problem cleaner. Okay, so e to the x on the left, nothing changes for now. 2 times 1 over e to the x, because we do the reciprocal, and the positive exponent, the negative exponent becomes positive exponent. When you have the rational or the denominator, clean it up, or the same concept, make the problem look cleaner or more convenient for us to deal with to get to the end result or the solution. So multiply all by e to the x to get rid of the denominator. And we know that the e to the x never be 0, because that's the range of the exponential function. So multiply all by e to the x. We get e to the x times e to the x equals 2 plus e to the x. E to the x times e to the x, that's e to the 2x. Okay, equals 2 plus e to the x. Now, it looks like not pretty, right? It doesn't look pretty. So it can be done by treating them similar to the way that you treat with the quadratic equation. So we move all terms in one side and see how can we manage after that point. At this point, we have the equation on the left-hand side, 3 terms, and we see this equation, quadratic-like equation. Okay, so I'm going to put a note here, is quadratic-like equation. That means we can treat it. We can treat it similar to the way that we treat the quadratic equation. So by letting this quantity as something to the power 2, or we can write it as e to the x quantity squared minus e to the x minus 2 equals 0. And then we factor like what we treat and how we treat the quadratic equation. So e to the x times e to the x give us e to the x quantity squared. And then negative 2 is from the value 2 and 1 multiply. The middle side is negative. That means the sign of the larger quantity is the same as negative. So going to be negative 2 times positive 1 to obtain negative 2. And let's double check the middle product negative 2. The outer product is plus 1, so we get the right factor. So, and after that, sorry, it's jump. And after that, we can solve for x. Say the first product, we have e to the x minus 2 equals 0. The second one, we have e to the x plus 1 equals 0. Solve the first one, e to the x equals 2, or x equals natural log 2. The second one, e to the x equals negative 1. Recall the exponential never be anything non-positive or even 0. It cannot be happen. So this case is not possible. So now we get the intersection at x equals natural log 2. Okay, we got the left bound 0, the right bound log 2. How do I know the left and the right? I pretend like I draw the bar here, and then my bar with the width as the delta x. If I move my bar to the left and to the right, the upper curve stay the same. I mean, stay as upper graph. The lower graph stay as lower graph for the entire moving process. Okay, so that's confirm me that it's about with respect to x, and x from 0 to natural log 2. And that will help you set up the definite integral to find the area. The area bounded by these three graphs is set up as the definite integral from 0 to the natural log 2 of the upper limit. The upper is the one, the 2 times e to the negative x plus 1 subtracted by the lower. This is the lower. The lower is e to the x. And with respect to x, okay, that's a setup. And then clean up to make it ready for the next step. Take away the grouping symbol. In this case, nothing to do to compare to find the light term or no light term basically. And just keep going by finding the antiderivative. The first one will get 2 times e to the negative x divided by negative 1, because we use the chain rule here, not the chain rule, the use sub technique over here. Okay, and then the antiderivative of 1 with respect to x is x. Antiderivative of negative e to the x is negative e to the x, and then gonna replace the lower upper limit into the expression. So lower limit 0, upper limit natural log 2. The first quantity, if you rearrange, gonna have negative 2 divided by e to the power x, because the negative side is of the power is the reciprocal of the positive exponent. So replace with the natural log 2 for the first round of substitution. And then minus e to the natural log 2. And then the second one replace with the 0. And negative 2 divided by e to the power 0. And then plus 0 minus e to the power 0. After you clean up everything, the answer will come out as natural log 2 as a final result, or the area bounded by this graph.